Hi, my name is Osama Nasir, and I'm a PhD student at Brown University. I'm delighted to be virtually here with you today and present our work on disruption-free update releases at Facebook. Everyone is familiar with software updates in one form or another. An application like the browser gets updated and requires restarting the specific application. The updates and the corresponding application restart are essential for improving the experience and integrity of the system by adding new features, fixing bugs, and upgrading security and configurations. Meeting the performance and security requirements for billions of Facebook users is no easy task. Owing to the hundreds of services and tens of thousands of developers working on products, we observe the proxy and server code to constantly evolve. Consequently, millions of globally distributed proxy and application servers are restarted very frequently at Facebook. The figure shows the typical number of restarts in a week. While the proxy servers are restarted 3 to 4 times on median, application servers are restarted hundreds of times a week. The fast pace is due to the adoption of continuous release philosophy, where code changes are pushed to the production deployments as soon as possible. Consequently, the number of restarts has increased from once per week in 2007 to hundreds of times today. This roughly translates to restarting the server tier every 2 hours every day. Unlike the case where restarts can be delayed for days or weeks, the code updates and restarts at Facebook needs to be done right now. Now, the objective behind continuous release is to deliver code safely and quickly to get fast feedback. The problem is not unique to Facebook only and is also observed for other companies like Yelp, eBay, Salesforce, and Uber, among others. Although this problem is of interest to most global scale companies, we observe that the commonly used solutions are built around ad hoc strategies. Most teams still resort to using the old days sleep and failed health checks routine. A restarting instance sleeps for a time duration called draining period, fail health checks to avoid getting new traffic, and wakes up once the restart is done. To see why people are using such ad hoc strategies, let's take a look at the existing techniques. Traditionally, there are 3 ways for releasing updates. Let's assume we want to update the server application running on some machines and they are fronted by a load balancing layer. Blue-green deployment relies on over-provisioning the cluster and requires 2 sets of physical machines or VMs. Updates are released to one set of machines, and once they are restarted and initialized with a new code, the load balancing layer routes the user traffic to the updated servers. This technique is supported in frameworks like AWS Code Deploy and Kubernetes. The second technique, called rolling updates, incrementally updates the machine in batches. A number of machines are taken out of rotation, and the server applications are restarted. Once they are ready with the new code, the load balancing layer starts routing traffic back to them. This approach is supported by a host of frameworks and proxies like Envoy, Nginx, among others. The third approach, commonly called hot restart, builds on the idea that we don't necessarily need to make the machine hardware unavailable for traffic. Let's see how HA proxy does this. A machine is running an out-of-date version of HA proxy and needs to restart the application. HA proxy spawns a parallel proxy process with the updated code and starts listening to the same ports as the old process. The old process goes into a draining mode and starts shedding its connection. Consequently, one active proxy process is always available to serve the traffic. The Linux kernel provides multiple features like SO reuse port that makes such transactions possible. Now, the traditional approaches are suboptimal along multiple axes. First, there's a huge overhead and cost of maintaining 2 sets of machines for the blue-green deployments. The approach may not be practical for edge and in-ISP deployments where the number of machines is much more limited. For rolling updates, the restarting servers are not available to process any new connections. We tried this strategy for a few edge clusters, and the figure shows that the CPU capacity degrades proportionally to the percentage of machines restarted. Hence, there's a downtime for some servers. There may also be indirect implication in terms of inflated tail latency due to constant resources. A possible solution is to release updates for very small batches, but this makes iteration slow and is a major hindrance to frequent release. The Linux kernel has come a long way in improving the socket sharing among multiple processes. However, it's still limited for UDP. We tried hot restart at production edge clusters and observed that the updated proxy process receives the packet destined for the new as well as the old process. This behavior is due to the connectionless nature of UDP, and the kernel alone cannot differentiate between UDP packets destined for the old or the new proxy process. These misrouted packets leads to errors and termination for the old transactions. The figure summarizes our experiment with hot restart and shows that more than 10,000 UDP packets suffer this misrouting for every proxy instance. Further, services like Facebook Messenger mostly have long-lived persistent connections, and they outlive the draining period. Hence, they face disruption in form of connection terminations. The sudden termination for large crowd of users trigger reconnect storm. This effect is shown in the figure where there is a surge in the number of new connections at the end of training period. At multiple times, ISPs complained about the congestion at the cell tower due to the sudden reconnections. Additionally, there's an overhead of rebuilding the state for these terminated connections. We observe up to 20% surge in CPU usage at the backend for rebuilding the TLS state. With so many negative implications and risks for a release, the question is how to release the updates while ensuring zero downtime, fast iterations, and no disruptions. Next, I'll give a brief overview of the infrastructure and identify the insights that can help in answering this question. Facebook infrastructure includes two classes of deployments. Edge points of presence, or POPs, are distributed across the globe and are closer to the end user. At the other side, the data center houses the backend application servers. At each deployment, a layer of layer 7 load balancers called Proxygen manage the traffic. Proxygen at edge terminates the end user connection and forward the request to data centers. Proxygen at data centers forward it to one of the application servers. The application server tier comprises of multiple types of servers. For example, there is HHVM server for web and MQTT servers for public subscribed services like Messenger. Proxy and HHVM servers are the two components that frequently evolve and are the focus in this work. A consequence of this layered architecture is that there's a hierarchy between the components. For example, a downstream hop to a data center is a proxy at edge, and similarly, a downstream hop to an application server is a proxy at data center. We also observe that there's a single organization control over the user and application at one end, the data servers at the other end, and all the proxy tiers in between. Hence, there's an opportunity to coordinate the connection workflows within and across the components and clusters. Based on these properties, the intuition behind zero downtime release is to leverage Proxygen's position in the end-to-end hierarchy to coordinate the restart and prevent any possible disruptions. Motivated by these insights, Facebook uses three distinct mechanisms for zero downtime release. First, during the proxy restart at edge or data center, a mechanism called socket takeover initiates a parallel proxy instance and takes over the sockets from the existing instance. To tackle the deficiencies with hot restart like UDP misrouting, the new instance fronts and coordinates with the old instance to tackle any inconsistency with packet delivery. The termination for persistent long-lived connection to the old instance are avoided by migrating the connection to another healthy Proxygen instance. The restarting instance coordinates the migration with its downstream Proxygen by a mechanism called downstream connection reuse. At the HHVM server restart, the restarting server interacts with the downstream Proxygen to reconstruct the failed request. The requests are then replayed to other servers transparently to the end users. This mechanism is called partial post replay. Now, due to the diverse nature of the connections for the different services and different operational needs of proxies versus servers, the three mechanisms are required to satisfy the domain-specific requirements. While socket takeover works on a per-machine granularity and ensures zero downtime, the other two mechanisms involve coordination between different machines in the hierarchy. Downstream connection reuse involves relaying the connection to another instance to prevent end-to-end connection disruption, while partial post replay involves asking an intermediary to replay a request instead of asking the end user for the retry. I'll focus on socket takeover and partial post replay in the talk and encourage the audience to read the paper for in-depth detail of downstream connection reuse. Next, I'll talk about the details of how zero downtime is achieved for Proxygen. At steady state, a Proxygen instance is listening for new TCP connection through the listening sockets and has a set of active connections represented by the accepted sockets. Since UDP is connectionless and lacks listening sockets, Proxygen uses a set of UDP sockets for receiving packets for each service. The services are identified by the virtual IP or VIP, and the figure represents these sockets as UDP VIP sockets. At the restart, a new Proxygen instance with the updated code is spawned and the older instance enters the draining mode. The Linux kernel provides features of CMessage and SCM writes, through which a seamless takeover is possible, and using these features, the new instance take over the TCP listening and the UDP VIP sockets. Consequently, any further new connection will be accepted by the newer instance. The old instance is alive and still serving the older connection until the end of training period. Note that I've just touched the surface level details of socket takeover, and the low level details can be found in the paper. Now, each connection has some associated application state. The older instance contains the state for the existing connection, while the newer instance manages new connection and their state. If you look at TCP, the packets natively make their way to the older instance since the kernel knows about their respective accepted sockets. However, we observe a problem here for UDP. While UDP is connectionless, protocols like Quick built on top of UDP do maintain state for each connection. Taking over the UDP sockets would lead to the new instance receiving packets for the new as well as existing Quick connections. Since the new instance does not hold state for the existing connections, they will be terminated. To tackle this problem, socket takeover coordinates the packet forwarding between the two instances. Each instance has a unique ID, and that ID is encoded in Quick connection packets as connection ID. The updated instance fronts the older one for UDP. When it receives a Quick packet, it checks the connection ID to make the forwarding decision. If the connection ID matches the ID of the new instance, it will consume the packets. Otherwise, they will be forwarded to the older instance in user space. As a result, Quick packets are forwarded to the instance that contains their respective application state. Now, to an outside observer, the machine that houses the two proxy instances is always available to serve a new connection during the training period. Hence, zero downtime is achieved and there is no disruption due to the user space packet forwarding. Next, we move on to how disruption-free restarts are achieved for application servers in data center. The HHVM server manages two classes of workloads. The major workload is API calls, and they also serve HTTP post uploads. While API calls are mostly short-lived, the post involves uploading the data from the user to the backend servers over wide area networks. These connections are mostly long-lived, and they have the overhead of losing state if terminated. Now, one option to reduce the disruption for these servers is to use socket takeover. However, socket takeover is not the perfect candidate for the server tier because of two reasons. First, these machines have resource constraints and cannot run two parallel server instances. Second, even if socket takeover is achieved, the servers are allowed a very short draining period since their primary workload is short-lived API calls. As a result, the long-lived post will outlive the draining period and still get terminated. Now, consider the scenario when there is an active post request and the HHVM server X at data center restarts. A simple solution to prevent the user retries can involve requiring the downstream proxy agent to buffer the post data until request completion. If the request fails, the proxy agent can replay the buffered request to another healthy server instance. However, this design is suboptimal owing to the high resource overhead of buffering every single request data. To circumvent this problem, partial post repair designs a novel HTTP mechanism. The restarting server signals its restart intent to the downstream proxy agent and also send back the incomplete post data it has received yet. The proxy agent reconstructs the request and replays it to another HHVM server. Once the request is completed, a success code is sent back to the user. The restart is completely transparent to the end user and saves the user from resending the data over high RTT wide area network. Further, no data buffering is required at proxy agent. Next, I'll move to the evaluation. To evaluate this mechanism, we analyze historical traces for the releases at different globally distributed deployments. We further conducted the traditional rolling updates and hot restarts on 10 edge and 10 data center clusters. We restart the machines in batches of 20%. For hot restart, we use the state-of-the-art SCM writes and C message for passing sockets. We monitor several metrics. At operator side, we monitor cluster CPU capacity, request per second, and the time to completion for releases. For the end user connection, we further monitor connection termination and errors for various protocol and services. We are interested in three questions. First, what are the benefits over the traditional strategies? Second, what are the operational benefits at scale in terms of preserving the robustness of the system? And third, what are the resource overheads? In this talk, I'll be focused on the first and third question. Please refer to the paper for more evaluation results. First, we focus on the rolling update strategy. The figure presents the median CPU capacity during release across 10 edge clusters. We define the available capacity as the sum of available CPU for processing a new connection. The value is normalized by the total capacity measured without the restart, and this capacity also serves as a baseline. For rolling updates, we observe a decrease in available capacity that is proportional to the percentage of machines restarted. Facebook uses a training period of 20 minutes for the edge, and this capacity is effectively lost for that duration. However, for the zero downtime case, the available capacity is nearly the same as baseline. Although 20% of proxies are undergoing a restart, the overall available capacity is within 3% of the baseline, even at the worst case. This highlights the prowess of zero downtime release in terms of preserving capacity. These benefits are a major win, especially for edge and in-ISP deployments where the number of machines is more limited. Next, we focus on the consistency aspects for the quick connections. Here, we compare against the traditional hot restart. The figure plots the distribution for the number of quick packets misrouted for proxy gens at each minute of the restart. To recall, these experiments are conducted across 10 edge and 10 origin data center clusters. We observed that there are up to 20,000 packets misrouted for quick in a single machine at the worst case. The number of misrouted packets gradually decreases with time as the instance is in draining mode and the older quick connections are getting terminated due to misrouting. However, the user space packet forwarding for the zero downtime case significantly improves the consistency for quick connections. At the median, there are virtually no packets misrouted. We observe a very small number of misrouting at minute 1, but the number is insignificant. It is 100 times smaller than the traditional case. Finally, we analyze the resource overheads. The figure plots the system resource usage during the restart phase for machines in production edge cluster. The presence of 2 concurrent proxies and instance contributes to the cost and system resources, increased CPU and memory usage, and decreased throughput. Although the tail resource usage can be high, we observe it to only persist for around 60 to 70 seconds and is observed only for initializing the new instance. As the machine is still available and able to serve new connection, this overhead is a small price to pay for minimizing disruption. Next, I'll talk about some lessons from experience. The zero downtime release has been functional at Facebook for several years and has gone through multiple iterations. In the paper, we mentioned multiple war stories, and I will focus on just 2 in the talk. Socket takeover can lead to some very unintuitive scenarios. If bad code is rolled out, the common practice is to roll back to the last known stable version. However, this may not hold when socket takeover is used. Hence, we face a scenario where we have an outage, we roll back the code to fix the issues, but the outage is still there. A pitfall of socket takeover is that it introduces the possibility of leaking sockets and their associated resources. We observed a severe disruption where a faulty release led to proxy ignoring some of the UDP sockets. These ignored sockets were orphaned and were still functioning in the kernel view. Consequently, the kernel still sent them their share of packets. Machines in order of hundreds were affected and millions of connections suffered from timeout since proxygen was not reading data from the orphaned sockets. In another instance, the socket state was corrupted due to a kernel bug in UDP write path. Socket buffers were not cleared properly due to the bug and accumulated over time. It was very complex to debug this problem as the dashboard does not have any visibility into the event, and it eventually led to a system-wide failure to write any further UDP packets. For both the cases, a simple rollback does not solve the problem as the orphaned and the bad socket state persist across a restart. At the global scale, these issues become very hard to solve and greatly increases the debugging complexity. To tackle these issues, we recommend a strict monitoring of sockets within the system. The proxy should monitor metrics like queue lengths and failure counts for socket read writes to make sure that there's nothing bad going on. It is also essential that the receiving process acts upon each of the received sockets, either by listening to them or by closing any unused one. We further recommend adding a kill switch to the proxy to disable socket takeover at shutdown or restart so that the issues can be contained. So for example, if in the next release, socket takeover wouldn't work and the bad socket state wouldn't persist. In conclusion, I would like to say that the millions of servers are restarted daily and have negative implications along multiple axes. To tackle the disruptions, zero downtime release mechanism level the layer 7 proxy in the end-to-end path to mitigate or mask a restart related disruption. There are 3 mechanisms: socket takeover to improve availability, downstream connection reuse to reduce disruption for long-lived connections, and partial post replay to mitigate disruption for data uploads. These mechanisms have been active at Facebook for years and are used on a daily basis. Thanks for listening to the talk.